Okay, well, happy week 9, happy Monday. Thanks for coming to class and being here. Um, we'll take a look. Our topic today is randomization tests, and so the context that we're going to look at randomization tests is going to be for comparing proportions. And so first, I'm going to just kind of start off with just a classical example from intro stats. So this part is all review, but I'm going to kind of go through it quickly, and this will just be how do you compare proportions from two groups? Because I think this is a very relevant, this kind of test happens a lot. Okay, and there's lots of ways you can do it. One is a chi-square test. Here we'll do a two proportion z-test. I imagine you did this in either AP Stats or Stats 10 or whatever equivalent intro stats class you had. And so here, I'm just making up these numbers, but one example is, is the proportion of international students different for stats majors and data theory majors, okay? And so, again, just completely making up these numbers, but let's say I get a random sample of 150 students who are majoring in stats, and 75 of them are international students. So 75 out of 150, that's half the students, okay? And then let's say we get a random sample of 160 students majoring in data theory, and 64 of them are international students. So 64 out of 160 is what, 40%? And so we want to, hey, is that difference between 50% and 40%, is that significant? Okay, does that provide evidence that the proportion of international students is different for students in stats versus students majoring in data theory? Same kind of question can be applied to all sorts of other scenarios. It's election day tomorrow, okay? And so, you have different candidates and you have different measures and propositions, and it could be like, hey, does this group of people, does the proportion of people who support this whatever proposition or measure or candidate, is that different for this group versus that another group, right? If you look at this neighborhood, what's the proportion of people who support this versus this, and this neighborhood, what's the proportion of people who support that, right? Or, I think we can imagine just any kind of thing. Just imagine two different groups, and then you want to know, I'm going to ask them a question, and are we going to get the same response? The proportion of people who say yes to the question, is it going to be the same for both groups, or is it going to be different? And if it is different, is that difference significant? Okay, even just has opinions changed from 2020 versus today? Okay, if you ask the question, whatever question you can think of, and there's all sorts of questions, right? You can say, hey, is so and so too old? Whatever, in 2020 versus today, is that answer going to be different? Okay. All right, so anyway, what we can do is we can do a z proportion test. So again, this is what we've observed in our data. In stats, we have 150 students total, 75 are international. So our observed proportion p hat for stats is going to be 0.5, 75 divided by 150, okay? For data theory, I have 160 students total and 64, so I do 64 divided by 160. And I wrote p hat. I know data theory isn't math, but it's a little bit more math heavy, and just to kind of keep the symbols short and easy, I'm going to write p hat math, okay? I know data theory is not math, but it is definitely more math heavy, and that's going to, so we're going to write 0.4, okay? And so we're going to say p hat between stats and p hat data theory, 0.5 minus 0.4 is going to be 0.1, okay? So we want to know, is this observed difference of 10 percentage points, 0.1, is that statistically significant? The null hypothesis says that our two proportions are the same in the population, that if we were to look at all of the students majoring in stats and all the students majoring in data theory, that these two proportions, there's really no difference between them. Okay, our null hypothesis would say the difference in the populations, there's no hats here, just p stats minus p for data theory or math, that difference is zero. There's no difference. The alternative says, oh yeah, there actually is some kind of difference. It's something other than zero. Okay. If the null hypothesis were true, we would expect whenever I take random samples, I would expect the difference between these proportions to be something around 0. We got a difference of 0.1, 10 percentage points. Is that difference statistically significant? That's what we want to know. So this is how you would go about doing this. Maybe you remember this, maybe not, but it doesn't matter. We would say, hey, you know what? When you take random samples and you calculate the difference between these two random samples, the proportions in these two random samples, that can be modeled with a normal distribution where the mean is equal to 0, okay? Because if the null hypothesis were true, we would expect the difference when you take two random samples, we expect that difference to be around 0. Sometimes it's going to be greater than 0, sometimes less than 0, but if you did it a bunch of times, we expect it to be centered at 0. The standard error is just this ugly formula where you have to calculate p hat as the overall proportion of yes out of no answers and things like that. But again, we expect this difference to be centered at 0 if the null hypothesis were true. And we would go through a calculations. We could do p-value calculation, and the p-value is, what's the probability of getting your observed difference or something more extreme if the null hypothesis were true. So if there were actually no difference in the population, what's the probability that a random sample for stats would end up 0.5 and the random sample for math or data theory ends up only at 0.4 and you have a difference of 0.1? We want to know how often does that happen by random chance. Because we're interested in our alternative has a not equal sign, we're interested in either a positive or a negative difference. We're going to take the absolute value. Okay, so in our case we got 50% stats and 40% for data theory, so that's a difference of positive 0.1. But it would also be interesting to us, according to our alternative hypothesis, it would also be interesting if stats was 40% and math was 50%, okay, or data theory was 50%. We get a difference of negative 0.5 or negative 0.1. That's also interesting to us, and so we would end up with. So we're going to take the absolute value. Okay, both of these things are interesting, and so because both of these things are interesting to us, we use the absolute value. I'm going to just skip over this. You do your math, you get your overall p hat to be 0.44. You get your test statistic 0.1 divided by your standard error. Your standard error is 0.0565. This ends up with a z-score of 1.77. And when you calculate what is the probability of being greater than 1.77 and the probability of being more negative than negative 1.77, you end up with a p-value of 0.0768. 0.0768. This is kind of our diagram. Again, we're expecting a difference of around 0. We observed a difference of 10 percentage points, 0.1. So what's the probability of getting 0.1 or something more extreme, or negative 0.1 and something more extreme? And the area in these two tails is around 0.0384 each, so around 0.077. And so our p-value is what? Over 7%, a little under 8%, 0.0768. And if our alpha, our significance level, is 5%, our p-value is larger than alpha. And so the decision we make is if the p-value is larger than alpha, we do not reject the null hypothesis. And we would say the data we have does not provide evidence that the proportion of international students is different for stats majors and data theory majors. So that we're saying, yeah, if the null hypothesis were true, and if the proportion of international students in, I wrote math, but data theory and stats are the same, even if that were the case, what would happen? What would happen is we would expect my two samples to have proportions that are equal. When we did our random samples, we got one sample with 0.5 and the other sample with 0.4, a difference of 10 percentage points. And according to our calculations, yeah, a difference of 10 percentage points is not super common, but also not that unusual. A difference of 10 percentage points could happen by randomness, and it's going to happen with a probability of 0.0768. So it's not a huge probability, but it's not small enough for me to just say, hey, it's super unusual. And so we're going to say our observed difference of 10 percentage points might have been caused by randomness. We're not ready to say it was the result of anything other than randomness. And so we just we leave it at that, okay? This z-test that we did relies on the central limit theorem, because the z distribution is what? The normal distribution. And we're relying on the central limit theorem that says sampling distributions can be approximated with the normal distribution, okay? And so in order for us to use the central limit theorem, we need to have samples that are, quote, large enough. General consensus for large enough means you need at least 10 yes responses and 10 no responses in all the groups that you have. And so here we had 150 students in stats. 75 basically answered yes and 75 answered no for the question, are you an international student? And then the other, for data theory, we had 160 students, 64 said yes, which means 96 said no. Those numbers are also greater than 10, okay? So we have at least 10 yes and 10 no's. And so our samples are large enough. We can use the central limit theorem. We can use a z-test, okay? And in general, if you can just use a parametric test, just use a parametric test. Your life is generally easier, okay? You just kind of have to check your conditions. But if you don't have a big enough sample, then using a parametric test can lead you to the wrong p-value and thus lead you to the wrong conclusion. And so in those cases, you might need to use a randomization test. And that's where it takes us now. Let me go ahead and give you your first view quiz answer, which is the letter D. D as in dog. D as in dog. Okay? All right. I am going to play you a video on YouTube. This is from an old TV show called Mythbusters. I don't know if you ever watched Mythbusters. I'm like looking ahead into the future, and it's going to be like, I've never even heard of that show. But okay, some of you are nodding your head, so I feel like, oh, okay, we're still not like super out of touch just yet. but it is like what? This show is like over, I don't know, it's like 15 years ago now or whatever. It's a fun show, but they did a little bit of statistics. I don't know about it. Okay. But anyway, I have to pause the video. So thank you to the dozen of you who came to class. But the rest of you who are watching online, you're going to have to continue to the next video. And because if I play this and I record it, I'm going to get a copyright strike. So I got to stop here, okay?